Yes. Kuya. Class kan ilo chano. Oh, demonstrate dona. Class control puing ya. Yes, okay. So you can type in your roll number. So the first roll number I see here is roll number 003. So those of you who have typed before 003 may retype your attendance again. Day before yesterday, I had a program at MZU. So I requested our HOD to take care of my class slot, but he agreed to it, but he had a meeting, urgent meeting in the IQSC office. So without prior information, that class was cancelled. I'm so sorry about that. So as I promised, if I have to cancel my class, I will give out prior information. Now, today we'll start with this inverting amplifier. So the configuration for inverting amplifier is shown here in the PPT. I hope everyone can see the PPT by now. And yes, I see that I am audible also. Right. So this is your IC 741, which is your practical op-amp IC. And here again, pin number 7 is connected to positive power supply. This is denoted as plus VCC. So this plus VCC is usually 12-volt supply, and pin number 4 is again connected to negative power supply, negative DC signal, which is denoted as minus of VEE, which is actually 12 volt, minus 12 volt. So as I already mentioned earlier, this op-amp has about 22 transistor inside this op-amp integrated circuit, and in order to operate those transistors, this DC power supply is provided. And so far we have discussed op-amp in open loop configuration. Open loop means, as I mentioned in the previous class, open loop means you are not connecting output to input. Okay, so if you have if you take a simple op-amp circuit like this, you take an output from pin number 6 and you are giving input at pin number 2 and pin number 3, and pin number 3 is non-inverting input, and the voltage at pin number 3 is denoted as V1, the voltage at pin number 2 is denoted as V2, and pin number 2 is your inverting input. So the difference voltage VD is equal to V1 minus V2. So this is what your output will obtain. Output will be an amplification of your difference voltage with your open loop gain, OL. So open loop means you are not connecting output back to the input. Okay. Now we are coming to this inverting configuration and non-inverting amplifier and other configurations of op-amp, where you are now connecting output of this op-amp, which is taken from pin number 6 here, output of op-amp back to input here, output of op-amp back to the inverting input. The inverting input is pin number 2 as denoted here, and minus sign also. So output signal is connected back to the input, inverting input. So in this configuration, when you are connecting output of an amplifier to input again, then that circuit is called closed loop, or a circuit with feedback, a circuit with feedback. All right, now so inverting amplifier, the one shown here, is also one of such circuit with feedback. Just 1 minute. Just 1 minute. I need to respond to my father. All right. So here the circuit element used for connecting the output to the input is a resistor here. As you see, this is a resistor symbol. This is a resistor symbol. You are connecting output to input via one resistor, and that resistor is called feedback resistance, denoted as RF here, feedback resistance. Right. So inverting amplifier, the non-inverting input terminal, pin number 3 here, non-inverting input terminal, the voltage at which is denoted as V1. Non-inverting input terminal V1 is connected to ground. So whenever there is this triangular circuit symbol here, this is same as writing something like this. Okay, this is a symbol for ground connection. Ground connection means it is connected to 0 volt. So the voltage of like earth line is considered as 0 volt. So those voltage which are above the voltage level of this earth line is considered as positive voltage, and below that is considered as negative voltage. So we are connecting to ground. So that means in inverting amplifier shown here, the non-inverting input, which is your V1, is already 0 volt because it is grounded. All right. And in addition to connecting output signal to inverting input here, pin number 2, we are also supplying input voltage VI, denoted as VI here, input voltage VI, via one resistor called input resistance here. I think you can see the one I circled here, RI. RI is called the input resistance. So via this input resistance, you are supplying your input voltage to pin number 2, the inverting input. Okay, so when you are giving input signal to inverting input, inverting terminal, that is pin number 2, the configuration shown here is known as inverting amplifier. So as the name implies, the output will have reverse phase in comparison to the input. So that means if your input signal, your VI is your input signal, if your VI is negative voltage, your output signal will be positive voltage. That's the process of inverting. Okay, so inverting input, whatever voltage signal you are giving to this inverting input, it will be inverted in the output section. So this is the configuration. Now from the op-amp this characteristics, we already know that output voltage is open loop gain multiplied with difference voltage. So as I said, if VD is positive, you are going to multiply with 200,000, then your output voltage will be going to what is called positive saturation. This I have discussed. It cannot exceed your DC power supply of plus 12 volt. So if VD is negative, your output voltage will go to what is called negative saturation, as the output signal cannot go beyond your negative voltage signal of minus 12 volt. All right, so it will saturate slightly lower than plus 12 volt and minus 12 volt. So in some configuration, the plus VCC and minus VCC is taken as 15 volt and minus 15 volt. So it doesn't matter. So here, if you connect plus 12 volt and minus 12 volt, it will go into either positive saturation or negative saturation depending on your VD. But now if you have this feedback circuit, let's say you are giving certain voltage signal to this input through this inverting terminal pin number 2. And now if you're looking at this formula, VD is equal to V1 minus V2, and V1 being 0, you will find that your VD will be negative. If VD is negative, it will drive the output to negative saturation. So when it drives the output to negative saturation, see, your V out is here, and the voltage at this point is your V out. When it drives the output to negative saturation, you are feeding back that negative voltage to this signal here, and that will result into, if you're giving large negative signal voltage here, the VD will be turned into positive voltage signal, and that will again drive the output into positive saturation. So if you are considering like fractional, very small fractional seconds, it is supposed to I mean, the output voltage is supposed to flip between negative and positive saturation. But once you have this feedback circuit, this op-amp has a very interesting property that with the help of this feedback circuit, it will eventually set the voltage at pin number 2, which is denoted as V2, and the voltage at pin number 3, which is denoted as V1. It will set the voltage at the two terminals V1 and V2 as equal. Okay, so this closed loop configuration, this op-amp, when you have a feedback circuit to inverting input here, the voltage at pin number 2 and the voltage at pin number 1, voltage at pin number 3, which are denoted as V1 and V2, they are eventually almost instantaneously set to be equal. V1 and V2 are equal in a very like small fractional seconds. Now because of that is all because of this feedback circuit. So as you can see, like it is supposed to drive into either positive saturation or negative saturation, but with the help of this feedback circuit, it is supposed to flip between positive and negative saturation. But this actual op-amp, when it is in operation, it has a very interesting property that it will set these two voltages V1 and V2 to be equal. So instead of driving to flipping between positive and negative saturation, it sets V1 to be equal to V2 always. Right, it says V1 to be equal to V2 almost spontaneously. Now if V1 and V2 are equal, and we already know that the voltage at the inverting input V1 is 0 volt, so due to this op-amp feedback, this is property of op-amp with negative feedback, because you are connecting output to inverting terminal. So op-amp feedback circuit with negative feedback, V1 and V2 are always set to be equal to 0. So therefore you can see that V2 is also 0 volt. Okay. Now another thing that you should remember in what I have discussed, well, I discussed characteristics of op-amp, is that the input, the differential input resistance at the op-amp, at the input terminal of an op-amp is very large. It's around 2 mega ohm. Okay, input resistance is around 2 mega ohm. Input resistance is around 2 mega ohm in practical op-amp. For ideal op-amp, it is actually infinity, but for practical op-amp, it's 2 mega ohm. So because of this large input resistance, the current entering op-amp here, let's say I2, for example, the current entering op-amp IC here, which I denoted as I2, it is practically 0. Okay, because of large input resistance. 2 mega ohm. So like as you can see here, this voltage supply, when it supplies potential to this resistor, then via this resistor current will pass through it, and the current flowing in this arm will find a junction here. From this junction it can either go towards the op-amp IC, or it can go towards your feedback resistor. So feedback resistor is usually in kilo ohm. With the normal resistance used in this kind of circuit is in kilo ohm, either 1 kilo ohm, 10 kilo ohm, 22 kilo ohm, or 50, 100 kilo ohm, whatever, right? But the input resistance of this op-amp IC is 2 mega ohm. So at this particular branch point, instead of going towards this op-amp IC, it will go towards this feedback circuit. So if you apply Kirchhoff's law at this junction here, Kirchhoff's law, first law says that at any junction, the total number of current entering the junction equals total number of current leaving the junction. So if you look at this circuit carefully here, the current entering this junction is your I1. The current which is supposed to leave this junction is I2 and your IF. Okay, and also we know that I2 is 0. So you will find that your II input current is equal to IF. Okay, according to Kirchhoff's law, because your I2 is 0. II is equal to IF. Now, what is II here? So this point here, the voltage at this point is denoted as V2 here. And because of this feedback, negative feedback op-amp property, we have already said that V2 is also set to be 0. So what will be the current II expression here? The current II expression will be the voltage at this point, the potential difference across this resistor divided by the resistance. Okay, according to Ohm's law, V is equal to IR, right? So your II will be, see that your II will be potential difference, that is your VI minus V2 upon your RI. If you look at this circuit, the current passing through this resistor RI will be VI minus V2 divided by RI. Potential difference upon resistance will give you your current II, right? And similarly, what is the current IF here? The current IF here will be potential difference across this feedback resistor. So on the left side, the potential at this point is V2, and on the right side, the potential on the right side of this feedback resistor RF, the potential at this point is your V0. Okay, the potential at this point is your V0. The potential at this point is your V2. So potential difference upon resistance will give you your feedback resistance again. Sorry, your feedback current. Now your IF. Now if you follow that, IF will be V2 minus V0 upon RF. And we know that our V2 is 0. That means this will be your V0 upon RF, right? And also here we know that V2 is 0. This your II will be VI upon RI. And from Kirchhoff's law, we have concluded that II is equal to IF. So that means your minus of V0 upon RF will be equal to VI upon RI. So voltage, output voltage upon input voltage will be equal to minus of RF upon RI. So what is this output voltage upon input voltage of an amplifier? This voltage ratio, output to input voltage ratio, is known as gain of an amplifier. Okay, so gain of an amplifier, which is output voltage upon input voltage, is what you call it as a closed loop gain. Okay, closed loop gain of this inverting amplifier. So here I denoted it using SCL. CL means closed loop gain. So the inverting amplifier has a circuit with this negative feedback here. So closed loop. Closed loop gain is output voltage upon input voltage, and the closed loop gain is equal to minus of RF upon RI. So what a very interesting conclusion we can see here from this calculation is that this operation amplifier, without your without your feedback circuit, the gain of that amplifier is more or less fixed at 200,000, right? But now once you have this feedback resistor and one input resistor, the gain of your amplifier is now negative of ratio of the feedback resistor upon input resistor, input resistance. So if you choose your feedback resistance to be, let's say for example 20 kilo ohm, and your input resistance to be 1 kilo ohm, then the closed loop gain of your inverting amplifier will be minus of 20 kilo ohm upon 1 kilo ohm. So kilo ohm and kilo ohm cancels out, and then your gain will become minus of 20. Okay. The gain will become minus of 20. And similarly, if you choose your what is that? I need a blank space. Okay, let me write something here. If you choose your feedback resistor to be, for example, 15 kilo ohm, and your input resistor to be 10 kilo ohm, then the closed loop gain of your inverting amplifier, which is minus of Rf upon Ri, this will be equal to minus of 15 kilo ohm upon 10 kilo ohm. So this will be having a gain of 1.5 minus of 1.5. It'll have a gain of minus of 1.5. All right. So the advantage now is that once we have a feedback circuit like the one shown here, by choosing the resistance value of R1 and RF, you can design your amplifier with the desired value of gain, the desired value of gain. Instead of having a fixed open loop gain of 200,000 with a feedback circuit, we can design this amplifier depending on our requirement, right? Now I think I should not do much calculation today. Now this is one example which I want you to work out. So this is one simple example. Here you find that the feedback resistor RF here is your 100 kilo ohm, and the input resistance here in this case is 10 kilo ohm. All right, this is your 100 kilo ohm. RF is 100 kilo ohm. Now what is calculate the output of the following circuit. V naught. This is V naught. You have to calculate. Okay. So how do you calculate V naught? This is a very simple example. Let me quickly do it. If in order to calculate V naught, what you need to do is first you need to find out your closed loop gain. Here, if you look at this circuit, the input signal, which is plus 2 volt, is supplied to inverting input terminal. So if this is given to inverting input terminal, then this is your inverting amplifier. Okay, this is your inverting amplifier. So if this is an inverting amplifier, from the previous calculation here, we already see that the closed loop gain of an inverting amplifier is minus of RF upon RL. Oh, hello, RC again. Oh, class cái này mấy cái anh dưới thị trường. Issue. Change some read per month in the ten upgrade thì more can ERP memory. Cái mà cái mà cho principal IBM. Memory lo full vang ni mo kan AWS kan subscription memory lo full vang ni mo kaka principal office ko online ni mo chu ania eng loin tiang miang za som read per month in upgrade the memory upgrade thì mo chu mo cái mà đi xuân sim ngot kha fellow mo college silon sia ole what cái mà ni IT committee WhatsApp group ka lo ron chum ngo mi dang college sila sum sum kai mai ni sia this on kema se bud lo or la ka lo ron lok don ne lo nga chang lok me ro o ka lo khil mai do ne ka lo ti pu nga IT committee ga lo ron pha dang IT committee principal pom tho mo o le class kon chu pha dang so your closed loop gain with this inverting configuration is minus of RF upon RI. So simply here you find the closed loop gain in this circuit. This is 100 kilo ohm upon 10 kilo ohm. So your gain will be minus of 10. Now your input voltage is plus of 2 volt. So your closed loop gain formula is open output voltage upon input voltage. So output voltage will become ASCL closed loop gain into input voltage. So your closed loop gain is minus of 10 into VI is plus of 2 volt plus of 2 volt. So this is minus of 20 volt. Okay. So the output voltage is supposed to be minus of 20 volt. Now, one thing you should remember here is that here your negative signal voltage is, sorry, in your negative DC power supplied here is minus of 15 volt. So it cannot go below this minus of 15 volt. It will saturate at minus of 15 volt. Okay, it cannot exceed that minus 15 volt. It will saturate at minus of 15 volt. So that's a very simple example. And now, I want to conclude with this non-inverting op-amp because I have some other urgent appointment. So this non-inverting op-amp also is similar to the inverting op-amp that we discussed. Here, the only difference is that instead of supplying power or DC signal, instead of supplying input signal to this inverting input, you are now supplying input voltage, which is denoted as VI here, to your non-inverting input. Okay, you are supplying to the non-inverting input. So the inverting input here is connected to ground. This is 0 volt. Okay, connected to ground. So if this terminal is 0 volt, then here this terminal is 0 volt, and here this non-inverting input is denoted as V1. Inverting input is denoted as V2, right? And that is the usual notation we use for this op-amp. So your V1 here will be equal to input signal, which is your VI. V1 is equal to VI. And due to the reason I discussed before, with the help of this feedback resistor RF, this op-amp will set eventually into the condition that V1 and V2 are equal. So with the help of this feedback circuit, the voltage at the two input terminals, that is pin number 2 and pin number 3, are always set to be equal. In op-amp operation, whenever you have a negative feedback like the one shown here, that is output signal connected to negative input terminal, output signal connected to inverting input terminal, whenever you do that, the voltage at non-inverting terminal V1 will always be equal to the voltage at inverting terminal V2. Okay, so this means that if V1 is equal to V2 and V1 is equal to VI, then your V2 is also equal to input voltage VI. Right. Now again, for the same reason that we discussed before, the current entering or coming out from this op-amp is 0 because of this high input impedance. Therefore, the equation that remains valid is II is equal to IF. IF is the current which is passing through this feedback resistor. So this side is ground, means the current is flowing in this direction. This side is ground. So you can see that the direction of current is denoted like this. It is reverse to the direction that we discussed in the case of inverting op-amp. Now, what is your II? II is again very simple. The potential difference between these two terminals, that is your V2, the potential at this point is V2. So this junction, the potential is also V2. V2 minus, this is 0 volt upon RI. So this is your V2 is what? Your input voltage VI upon RI. And now what is the current across this feedback resistor? The current across this feedback resistor will be the voltage at this point minus the voltage at this point divided by the resistance. Okay, IF will be equal to V naught minus V2 upon RF. V naught minus your V2 is equal to VI that we discussed before upon RF. This is your IF. Now put in this equation, they are supposed to be equal this and this. So then you get your V naught minus VI upon RF equal to VI upon RI, VI upon RI, which is V naught minus VI is equal to RF upon RI into VI. So my handwriting is a little bit poor, but I hope you can still read what I'm writing. V naught will be equal to 1 plus RF upon RI into VI. So your closed loop gain in this configuration is now output voltage upon input voltage equals to 1 plus RF upon RI. All right, so your closed loop gain in this configuration, that is the inverting, non-inverting op-amp configuration. When you feed your input signal to the non-inverting input, the closed loop gain is 1 plus RF upon RI. So if you choose your RF to be, let's say 40 kilo ohm, and if you choose your RI to be 10 kilo ohm, then the gain in this case ACL will be 1 plus 40 kilo ohm upon 10 kilo ohm. So then this will be having, your op-amp will be having a gain of plus 5. So in this non-inverting amplifier configuration, the closed loop gain is always positive. Closed loop gain is positive, plus 5. 4 plus 1 is plus 5 simply, right? So the difference in here with this inverting configuration is that in inverting amplifier, your gain is having a minus sign here. Because of that, the input voltage will be flipped at the output, and in the case of this non-inverting, the gain is always positive. So if you are supplying a positive input signal here, output also will be positive. If you are supplying negative input signal here, output voltage V naught also will be negative. That's what it is, right? So please calculate the gain for this, the second one. The first one, I'll discuss it in the next class. Can you tell me what will be the gain here? I think you can calculate here. Gain of the amplifier here in this case will be 1 plus, this is non-inverting because inverting input is grounded and you are supplying input signal here. Okay, so 1 plus RF upon RI. So in this case, 1 plus 75 kilo ohm upon 15 kilo ohm. So 1 plus 75 upon 15. So if you look at the circuit and see the resistors there, from there you can simply calculate the gain of your circuit. So this will be having a gain of 6 plus 6. Okay. If your input signal VI is if your input signal is minus of 1.5 volt, output will be closed loop gain into input signal. Here your gain is plus 6 into minus of 1.5 volt. Therefore, your output will be 6 into 1.5. That will be minus of 9 volt. So there is no flipping of the sign of the signal, the sign of the signal supplied to this op-amp. So if you are supplying negative voltage, you are getting negative output voltage. Okay, so that's how this kind of op-amp amplifier works. It amplifies without altering the sign here in this non-inverting. And in the inverting amplifier, even though it amplifies depending on the gain you choose, but it flips the voltage. Positive voltage flips to negative voltage and vice versa. So I'll stop here. Tomorrow, I think I can take class in the afternoon because I will not be having any practical class. Tomorrow, I think I will be free to take class around 2 p.m. If you are free, we'll do that. We'll stop now.